Okay, in this tutorial, we will be looking at the unit load method for circular beams, right? In the last class, we were dealing with straight beams, like for example here. Okay, what do I mean by straight? You see, this coordinate system, right, is linear, so it only moves in a straight line. Whereas this coordinate system that we'll be dealing with must follow along the curvature of the segment. Therefore, this will be curvilinear. Curvilinear. Okay, so in principle, it's the same. Okay, same steps as the previous tutorial, except there are a few minor adjustments. But I will show you as we go through the example. Okay, so let us read the problem. A uniform curved beam ABC of radius r is fixed at NC and free at NA. So free means it's not built in. Okay, see, A is touching the air, whereas C is built in, right? It's built in into the wall. So you imagine this beam as a metal arc welded into the wall, right? As a metal arc welded into the wall. So it's built into here. Okay. For your information, for built-in points, right, there will be reaction forces, horizontal and vertical reaction forces, and reaction moments. Okay. So what I mean is, if you draw the free body diagram of this beam, okay, if you draw the free body diagram of this beam, so you need to remove it from its surroundings. The surroundings also include this wall. Okay. So you only draw the beam. Okay. You must not include the wall. Draw this force. Okay. So wherever it contacted something, right? See, it contacted this wall at first, but now it doesn't. So wherever you remove it from a point of contact, you must reveal the reaction forces. So there'll be a vertical, horizontal, and reaction moment. Okay, so these are reaction forces. Okay, in contrast, if the support is not a built-in end, but rather a simple support, okay, if I draw the free body diagram of this beam, so I only draw the rectangle without the triangle. See, it contacted these two triangles at first. But now, after I draw the free body diagram, I remove the triangles. So wherever it contacted the triangles, you must draw the reaction forces. So for simple supports, it is only vertical forces. No reaction moments, and no horizontal reaction forces. Okay. Okay. So what they want is to find expression for the vertical and horizontal displacements at A, and also the rotation at A in terms of these parameters. Okay, so what must we do? So let us see. The first thing first is we start with the unit load method equation. So this, okay, and then we replace this with the complementary work. So complementary work for beams, right, is this. Sorry, complementary strain energy is this. Okay, so I need to do integration over several segments. So can I do an integration from A all the way to C in one shot? No, I cannot. Why? Because there are several segments in this beam. How do I know there are several segments? Remember, to identify segments, right, there must be a force change or there must be a beam change. So let us start from the the free end. You can start from the free end, or you can start from this fixed end. Okay, but it is better to choose the free end. Why? Because if you start from the fixed end, right, you must care about the uh reaction forces. So there will be a reaction force here, a reaction force here, and reaction force here. You will need to solve all these forces. So do not choose the built-in end. Always try to choose the free end. Okay, always try to start from the free end. Okay, so let us start from the free end and walk along the beam. As we walk along the beam, ask yourself, is there any force change or is there any beam change? When I mean by beam change, I mean, is there any changes in E, I, or cross-section area? So let us check. So I walk along this beam, okay, no force change, no beam change, no force change, no beam change. Ah, there's a force change, right? Why? Because now there's the existence of this force. So that means one integration is done from A to B, and then let us walk along from B to C. So is there any force change or beam change? No force change. Sorry. no force change, no beam change, no force change, no beam change, no force change, no beam change. Okay, so B to C is another separate integration. Okay, so we must do two integrals. Okay, so this is for, okay, let me write this down. This is for AB, segment AB, and this is for segment BC. Okay, now we must assign the coordinates, right? So they didn't assign us the datums here, so we must assign it ourselves. Because I told you AB and BC are two separate segments, so we will assign it like this. But take note, remember these are curvilinear coordinates. So my coordinate system will look like this. Like this. It follows along the curve of the curvature of the beam. Okay. And then because this is an arc, right? I will denote it with a different letter. I won't denote it with X. Okay. Because X is for linear coordinates. I will denote it with S. Okay. If you recall from AMATs, we used to use S to denote arcs. Okay. So this S refers to arc length. Arc length. Okay. So B to C is another different datum from here to here. Okay. So this is another separate coordinate system from B to C and from A to B. Okay. So I will not be integrating with respect to X anymore. I will be integrating with respect to S, the arc length. Okay. Yeah. So we will deal with the limits of the integrals later. Actually, let's deal with it now. Okay, let's deal with it now. So what are we going to do about this? The integral of the arc length. The integral with respect to arc length. Okay. So it is better to do this. It is better to replace ds with r d theta. How do I get this? If you recall from AMAS many years ago, we learned this formula. S is equal to r theta. Okay, you learned this in a chapter called circular measures. Okay, circular measures. Okay, where you are first introduced to the idea of radians and arc length, radius, and area of sector. Okay, so S is equal to r theta. Therefore, ds is equal to r. So the radius is constant throughout. See, the radius is constant throughout here. So it's r. Okay, r. Then theta is the one that changes, right? Because as you move along the arc, it will change. So this is like, for example, 0 degrees, 1 degrees, 2 degrees, so on and so forth. So this one must be d theta. Yeah. So wherever you see ds, you replace it with r d theta. R d theta. Okay, so this will be maybe I r d theta, and same thing r d theta. Okay, so now we deal with the limits of the integrals. So let us pay attention to segment BC first. So segment BC, you pay attention to this angle theta, right? Theta, you're moving from here 0 degrees all the way to here, 90 degrees, right? So you're making a 90 degrees swipe, a 90 degrees sweep. Okay, so 90 degrees is actually pi over 2 in radians, right? We'll always be dealing in angles in radians. So 0 pi over 2. Okay, same with segment BC. So BC, this is theta. So you're starting from here, which is 0 degrees, and then you make a sweep all the way to here, 90 degrees, which is actually pi over 2 radians, right? So this is also 0 to pi over 2. Okay, so now the next step is we need to find these expressions, this, and this. Okay, so how do we do that? Okay, so Okay, let's clean up this diagram first. So remember, let's do for AB first. Start from the datum, go to somewhere in between, make a cut. Everything after the cut, you throw it away. Then, just at the cut, you draw the internal moments. So this is MAB. Okay, now you take moments about this cut to find moment equilibrium about this cut to find MAB. So sum of M equals to 0 for the segment AB. Now, let's see. Is there any loading on AB? There is no other loading other than MAB, right? See, MAB is the only other loading. Otherwise, there's no other loading applied to this segment. So it would just be positive MAB equals to 0. So we know MAB is equal to 0. If we know MAB is equal to 0, we don't need to find the virtual internal moment anymore. Okay? We don't need to find this anymore because this is already 0. Therefore, the whole thing of this is equal to 0. Okay, so we only need to do this integral here. Okay, so let us find MBC. So we start from here. Okay, go to the middle, make a cut, throw everything away. So what you're left, right? What you're left is only this part of the beam. Okay, this part of the beam. Okay, so you draw the internal moments. This is MBC. Okay, and then you take equilibrium about this cut. Okay, so what loadings do you see on this highlighted segment? Well, you can see that there is this, right? W. Okay, so we need to find the moment due to W about the point of the cut. Okay, so that means we need to take force times perpendicular distance away from the cut. Okay, force times perpendicular distance away from the cut. So W is in this vertical line, right? This is the line of action of the force. Then the cut is over here. Okay, so we need to find this distance from the cut to this vertical line. Okay, this perpendicular distance. So how do you do that? Well, what you do is you start from the center of the circle, draw the radius here. So you know this is a length of r. You know this makes an angle of theta. Well, now you have a right angle triangle, right? This is a right angle triangle. So you have to do some trigonometry. So with respect to theta, this dotted horizontal line is opposite. Okay, let's label this as D. So this is D. So we know that D is opposite, R is hypotenuse, so we need to use sine. So sine theta equals the opposite over hypotenuse, and therefore D is equal to R sine theta. Okay, so we know that this moment arm is actually R sine theta. So the moment due to W is equal to W times R sine theta. So let's take moments equal to 0 about BC. So first we have the internal moment, right? The internal moment MVC. Okay, what else do we have? We have W. So W exerts a anti-clockwise moment. So see, MBC is anti-clockwise. Therefore, I'm saying that anti-clockwise moments are positive. So since W is also exerting an anti-clockwise moment, therefore it's positive W R sine theta equals to 0. Right? That's the only other load in this segment. Yeah. Okay, so MBC is equal to negative WR sine theta. Okay, then we need to find the virtual internal moments. Again, we don't need to find the virtual internal moments for segment AB anymore because big MAB is already 0. Therefore, you don't need to find small MAB. Okay, so small MAB is the same case. Okay, so you have the same beam, except now we're doing virtual load analysis. So this is unit load, right? We want to find the vertical deflection at A. So I must apply a vertical force at A of 1 unit only. So this is 1 Newton. Okay. Again, we don't need to care about A to B. We only need to care about B to C. So again, you start from B, you go to somewhere in the middle, make a cut, throw everything away. You only care about this remaining piece. Okay. Now we want to find the internal moment MBC. Okay, so you take moments, sum of moments about the cut, M equals to 0 for BC. Okay, so what is exerting load on this segment? We have this 1 Newton, right? This 1 Newton exerts a moment also. So this is the cut. We want to find the perpendicular distance of the 1 Newton force away from this cut, right? So we want to find this horizontal distance. So we know from this center to here is already the radius, right? We want to find this distance here, right? Which is not the radius, okay? So this is theta, this is r. This distance is the same as this horizontal distance, right? Yeah, yeah, okay. So yeah, we know that this is r sine theta from earlier. So that means this entire distance will be r plus r sine theta. Okay, so the moment due to this 1 Newton force will be, let's see, anti-clockwise, so it's positive. So positive 1 times this, right? So force times distance. Yeah. So we have MBC plus force times distance. Yeah. So MBC is equal to negative this whole bracket. Okay. So now we can substitute this and this into the integral, right? We want to substitute it in the integral here. So let us go ahead and do that. So delta y, so the vertical deflection is equal to the integration of MBC, MBC, EI, R d theta from 0 to pi over 2. Then we make the substitution. So big MBC is this negative WR sine theta multiplied by negative R plus R sine theta divided by EI times R d theta 0 to pi over 2. Okay, so let's expand everything in the bracket. Okay, so let's also deal with all the constants first. So you see, negative times negative is positive, so we can cancel them away. Then who else do we have? We can take out this 1 over EI outside the integration. So we have this. Okay, and then what I'll do is I'll expand this term to him and to him. Okay, so I have WR, and also don't forget to expand this to him and to him. So let's do this one by one. Okay, so WR square sine theta plus WR square sine theta. Okay. Actually, I can pull this R outside here too. D theta. Okay. Then I can factorize WR square, WR square. Wait, this should be square, right? Because sine theta times sine theta is sine squared theta. So I can factorize WR square. So WR square times R will be WR cubed EI. Okay. So now we're only left with sine theta plus sine squared theta d theta 0 to pi over 2. Okay, so you can perform this integration by a calculator and you should get 1.7854 times WR cubed over EI. Okay, the answer they give you is 1 plus pi over 4, right? But if you put 1 plus pi over 4 into the calculator, right, you should get my answer. So this is 1.7854. Yeah, it's the same thing. Okay, now we want to find the horizontal deflection. So the only change that you need to make for the horizontal deflection is MBC. I mean, the virtual MBC. This one can maintain the same because the external loads don't change. They're only the unit load changes, right? Because now we're looking for the horizontal displacement. So what you're changing, instead of a vertical unit load, we will change to a horizontal unit load. Okay, so it'll be 1 Newton this way. Okay, so let's do the horizontal analysis, the horizontal force analysis. So it is this. So this is a 1 Newton load. Wait, let me put the. Oh, the direction I chose is this. Is this. Doesn't matter if you chose that direction, you'll just get a negative of my answer. Okay, why do I know it's left? Because when I apply W onto here, I know that my arc, right, the resultant shape will be like this. So I know it will go to the left. So if I know it goes to the left, then I'll apply my unit load to the left. Okay, just using a matter of common sense. So, okay, don't forget, you must remove this load. Now we will, see, we can ignore AB because AB, the real load is 0. So we only need to do BC. So again, you start from here, you go to the middle, you make a cut, throw everything away. You only pay attention to this segment. Okay. So take moments about this cut. So don't forget the internal moments here, MBC. So what other loads are there? We only have this 1 Newton load. Okay, this 1 Newton load here. So remember, moment is force times perpendicular distance, right? The perpendicular distance is this dotted line. Okay. Okay. It's this vertical dotted line. So how to find that distance? Well, you know that this is r, right? This red line is r. This is theta. And you know that this vertical blue line is the same as this vertical red dotted line, right? So this falls in a right angle triangle. You know that with respect to theta, in this right angle triangle, this is adjacent, this is hypotenuse. Adjacent and hypotenuse means use cosine. Theta equals to, let's call this distance d. D over r, meaning d is equal to r cos theta. Okay, so we know that this distance is r cos theta. So to get the moment due to this 1 Newton force, it'll be 1 times r cosine theta, right? Force times distance. So m equals to 0 for BC. So we have positive MBC. Then this 1 Newton force exerts a anti-clockwise. Yeah, anti-clockwise. So it's also positive. So positive 1 times r cos theta equals to 0. MBC equals to negative r cos theta. So what we do is we substitute this into the integral, right? So now it's delta x because we're finding the horizontal deflection. Okay, from 0 to pi over 2. So MBC BC times MBC over EI times R d theta is equal to, okay, so what is MBC from earlier? I can't remember. Oh, this, negative WR sine theta. Negative WR sine theta multiplied by, okay, MBC is negative R cosine theta. Negative R cosine theta over EI. Okay, so let's simplify this. So negative times negative is just positive. WR times R times R. Okay, WR times R times R is WR cubed. You can also take EI outside the integral. So you have EI here. So what you're left in the integral is just sine theta cosine theta d theta 0 to pi over 2. Okay, you can do this integral in your calculator. So just do this part in your calculator. Then you should get that it becomes half actually. So half times this will be just there with 2 in the denominator. Okay, then lastly, you want to find the rotation, right? So rotation for the unit load analysis, you must apply a unit moment because rotation is related to moments. So you apply a 1 unit moment here. Okay, again, find the virtual internal moments at BC. You don't need to find AB because it's already 0 for the, yeah, it's already 0. So M, BC here. So sum of moments at BC is equal to 0. So positive MBC. Okay, so the 1 Newton meter unit load is in the same direction as MBC. So it's just positive 1 because 0. So MBC is equal to negative 1. Okay, then you can substitute this into your integral. So now we're looking for theta A is equal to integral from 0 to pi over 2. Okay, so I'm going to straight away make the substitution. I don't want to write the formula. So it'll be negative WR sine theta, right? So that's our big MBC, negative WR sine theta times negative 1 over EI times R d theta. Okay, so negative times negative is positive. WR times R is WR squared, over EI, I can take out the integration. And then what you're left with is just sine theta. Okay, you can do this by hand, but it's just faster to do it with a calculator. So in the end, this will become 1, okay, which is just that. Okay, and yeah, that's your answer. Okay. So it's just same steps as the last tutorial from let me just show you. Yeah, from here. Okay, same steps as this, except the trick here is we're dealing with a curved beam, right? So instead of ds, you replace this with r d theta. And where I get this? I get this from circular measures that we learned from AMATS long ago. Okay, so if you found this tutorial helpful, you can donate to me on PayPal. Thank you.